Okay, so in the course of this, we used 4 differently marked meter sticks, all of them 1 meter, but marked differently to measure the width of your desk. So we had this one with no lines on it whatsoever, just the statement that it is in fact 1 meter. Flip side of that was marked every 10 centimeters, so in there. Then we had this ruler, which marked numbered every centimeter and marked every half centimeter. And then on the flip side of that, it went by millimeters. And these are the numbers that we had reported with our first measurement with just the plain 1 meter stick, so you knew what 1 meter was. We saw a couple that were estimating, I can get to the nearest tenth. A couple and 3 or more that were more confident and saying, well, I know that's exactly 2/3 of a meter, for example, or close to it. As we go down, we start seeing more digits, at least in general, because you get more and more confident in your measurement. This is the essence of what precision is, and why we can't just say that if I put it down as 0.6 of a meter, that's the same as 0.6000000, because if this were a fraction, like so, we would naturally, because of our math backgrounds, think that that meant 0.6, and if we want to put 1,000 zeros after that, that's fine, because that's exact. However, we can't do that here. When we actually measure something, we are really limited by our tool. And you guys naturally found that just as going through with more marks, you got more and more confident, except for Hannah, she's always confident. Here is the rule for precision when you're using a tool. Find the smallest marking on it. So for this one, it's 1 meter is the smallest marking. You get to record or estimate 1/10 of that. So that means for this first measurement, it is permissible to record down to the 10th of a meter. It's not permissible to record more than that because our judgment isn't typically that good. We can judge to the 10th quite accurately, to the 100th, often not. So for these, our first one, we can't accept these because and this is something that's based on kind of international agreement for measurement. Based on that, we as humans can't have enough confidence in that last number. I'm okay with either of these. It tells me it's somewhere in between those two, and it probably rounds to whichever we thought. It's probably pretty close to the middle based on that. But we can round to this number. On B, that was the flip side. Now we're 10 centimeters. So that means we can estimate to 1/10 of that, which is a single centimeter or 100th of a meter. So good, fine, yep, we can do better with this tool, but not this well. So we can't accept that either. We can only go to the 100th. And we should be taking that. Now, what if this had fallen on exactly 0.6? What then?
You have to put a 0.
Yeah, 0.60 would also be an okay number. So if we thought this were really very close to that, 0.60 would be fine. I'm not judging correct or not right now. I'm just saying, what are we allowed to do? Now, on the back side of this one, what should we be estimating to? Thousandths. Exact thousandths? Let's look at the smallest one. So we've got centimeters marked, but really the smallest mark between two is half a centimeter. Scales like this are weird, frankly, because we should be estimating then to 1/10 of that. So we'd be going to 0.005s, but not quite thousandths. So we're not quite that tight. Now onto here, we actually have thousandths marked. Millimeters are marked. And it's very challenging now for a human eye to do this on its own, but we are allowed to measure up to 1/10 of a millimeter using this. That's a pretty daunting measurement for a naked eye. Sometimes we'll use magnifying glasses or even microscopes to be able to see better, and we're then allowed to go to the 1/10 of this. In many cases, if we are down to the millimeter with an unaided eye, I would say just record it at the millimeter. But the important part to remember with all of this is we can't go beyond what the tool allows us to. We got measurements of 0.7 and 0.6. Both of those are limited by the precision. It looks like we're probably closer to 0.6. And that's why we're not really allowed to go even more in depth, because the mistakes can occur so quickly and add up so quickly. Now let's use this one for another measurement to measure the thickness of the black tabletop as precisely as you can. This is pretty daunting, right? It's a challenge to measure that, especially to the millimeter you can probably do, but then if you want to get more precise than that, it's very, very challenging. And even the millimeter, I saw a lot of people struggling to hold the meter stick straight and make sure so we need another tool, and that's where this will come in. I'm going to show this to the camera and then pass them out. These are called calipers. They allow a few different measurements. You can measure the width of something by putting it in between these teeth. If you've got a gap, you can measure it here. You can measure the depth of a hole by extending this down into it. So they're pretty useful. These are called, now there are nice ones that digitally read out very, very precisely. But you're in public school. So this is actually good though. We have something called a vernier scale on this. And we are going to practice how to use this, how to read this vernier scale with these tools. So when we're using a caliper, we pinch it on something and then try and slide it off. And then we can take it off. We can even use this screw on the top to tighten it, but we don't usually need to. But if you really want to save a spot, you can tighten that and snug it. And we get, this. So now how do we read this? Well, we're going to get 3 digits off of this. The first 2 are pretty easy. Note, we've got 2 potential scales, inches and centimeters. We'll of course be using the bottom scale, which is in centimeters. So we're going to be saying a certain number of centimeters. The first 2, as I said, are pretty easy. Look for the left-hand mark on your caliper. We're going to go to the 10th, the nearest 10th that is smaller than that mark. So this one for me looks to point almost exactly at the 3.1 centimeters. So my first 2 digits there would be 3.1. If this were slightly to the left, but not to the next mark, it would still be 3.1 something. If it were slightly to, did I say what? If it were slightly to the right. If it were slightly to the left and in between the 3 and the first mark, we would say 3.0 something. So we always go back. Now this last digit is where the vernier part comes in. The vernier scale uses these marks down here as our last digit. But the funny part is, we just want to see which of these lines up really, really well with a line above it. We don't even care what line it is up there. What we care is which of these lines on the bottom lines up best with a line above it. And from my picture, it looks like either my very first or my very last line. Both of those line up really, really well. You might find something slightly different, and that's cool. What we want to do is start counting at 0, 1, 2, 3, 4, 5 is the middle one, 6, 7, 8, 9, 0. that is our last digit, whichever of those lines lines up best. So mine is my very first line, and I started at 0. So my last digit is 0. If this line had lined up best with whatever line above it, it would be 0, 1, 2, 3, 4.
So then would it be 3.14, would it be 3?
It'd be 3.14 in that case, and that would be if this were just slightly to the right. And of course, we're going to write units after that, centimeters. If it were slightly to the left, it would be 3.0, probably something close to 789.